I am Dr. Vikram Bali, Professor and Head at JSS Academy of Technical Education, Noida. The topic which we are doing today is finite state machine, and this topic belongs to the subject theory of automata and formal languages. So, first we will start with the introduction of finite state machine. As you can see in this slide, finite state machine is defined as a calculation model that can be executed with the help of hardware and software. Finite state machines are also called finite automata, and in short it is written as FA. FA stands for finite automata. It is the simplest machine to recognize patterns. It is used to solve the problems in the fields of mathematics, games, linguistics, and artificial intelligence. Specific input can cause specific changes in the state of machine. Now, this slide shows the formal definition of finite state machines. As in this slide, you can see that finite state machine is defined as M as a 5 tuple machine, and these are the 5 tuples, which are used to define the machine. So, Q stands for finite set of states, right. So, this capital Q stands for finite set of states. Sigma stands for the set of input symbols, and the input sigma stands for the set of the input symbols. Q naught is the initial state. Q naught is the initial state. F is the set of final states. Delta is the transition function, right. So, I again repeat here that finite state machine is defined as 5 tuple, and these are the 5 tuples which are used to define the finite state machine. Now, we have got two types of finite state machine. The first category is deterministic finite automata, and the second category is the non-deterministic finite automata. So, first we will try to learn about deterministic finite automata. In this slide, you can see the formal definition of deterministic finite automata, and in short it is known as DFA. In short, it is known as a DFA. So, DFA stands for deterministic finite automata, and it can be defined as again a set of 5 tuples where Q, sigma, delta, Q naught, F, right. Q, sigma, delta, Q naught, F. This is the formal definition of DFA. Before defining all these individual tuple, right, let us see what is the unique characteristic of this DFA is. In a DFA, for a particular input character, the machine goes to one state only. Now, this is the uniqueness, or this is the characteristic of DFA. In DFA, right, we have to remember that in case of a DFA, the machine goes to one state only. So, this is the differentiate which it makes it from the NFA, right. In DFA, it goes to one state only. The transition function of this DFA for every state, for every input symbol is defined as, you can see over here, Q, capital Q is the finite set of states. Okay, capital Q is the finite set of states. Next, we have this sigma, which is the finite alphabet set. It is the input alphabet set through which we make the input, which can be A, B, 0 or 1, right. So, the alphabet set. Third thing, Q naught is the initial state, Q naught is the initial state, right, which belongs to the finite set of states Q. F is the set of final state, which again belongs to Q, the set of states. Now, this is very important, the transition function, since in case of a DFA the major difference lies in the transition function. So, in this the transition function, right, the transition function delta is derived from Q state, the alphabet set and the new state, right. So, this is a very important this thing term that we need to highlight over here, the transition function for the DFA. Now, in this slide we can see the different building blocks which are used to draw the deterministic finite automata. Here you can see that the transition function can be represented by this transition state graphs. Okay. So, the transition function of deterministic finite automata can be represented by transition state graphs. So, every DFA, deterministic finite automata, will have a start state. This is a formal symbol for the start state, and the start state always represented by an arrow going into the state, right. So, this by if we draw a arrow into a state, it means that that particular state is a start state. Next, in all in the DFA, we have a final state, right, and the set of final states are always defined or represented by double circle. So, in case if in a diagram you see a double circle outside a state, it means that it is a final state. So, this is a final state, right, and in the transition graph in the transition graph you will have the different transitions. You will have state number 1 for which for some input it will go to state number 2, right. So, the different kind of transitions will be there in the graph. Now, in this slide we can see that we have drawn we have taken an example for the DFA, and the example which is given over here, it says that DFA with input as 0 and 1, which recognize all strings ending with 0, right. So, the language which is given over here is that strings in strings in which all the words should end with 0, right. So, here you can see that this is the DFA for this language, all strings ending with 0. The machine will start in state A, this is the initial state, state A, as there is a arrow going into the state. So, we can see that this A is a initial state, right. So, once the machine is in the initial state, we can have two inputs, right. The input can be either a 0 or the input can be a 1, right. You can see over here, once the machine is in the state A, which is the beginning, which is the initial state, which is the start state, we have a input 0 or we can have a input 1. If the machine has the input 0, right, it will go from state A to state B. For input 0, it is going from state A to state B, since in this language all strings ending with 0, the smallest word can be a 0, right. So, the smallest word which belongs to this language is a 0. So, for this 0, it is going from the initial state to the final state B, right. I have said in my previous slide that the final state is always represented by a double circle. So, you can see that over a B we have a double circle. So, this is the final state, right. So, in the initial state, if the input is 0, it will go to the final state. The second input can be 1. If it is a 1, it will loop back to itself. It means that it will remain in state number 1, right. So, once I am in the final state, which is a state B, right, I will be in the final state if I keep on reading any number of zeros. So, for that I have drawn a loop over here, right, because it says that all strings ending with 0, right. So, once in the final state, if I get a 1, I should leave the final state, because this language is for all the strings ending with 0. So, once if I get a 1, I will leave the final state and I will go back to the state number A, which was the initial state, right. So, we can say that we will remain in the final state only when we are reading 0 0 0, because this DFA is for one particular language, right, which says that all strings ending with 0, okay, all strings ending with 0. And one point that I would like to highlight over here, in case of this finite state machine, right, we need to take care of some fundamentals, right. So, every finite state machine will have a starting state, right, we cannot skip that, and it should, if it recognize a language, then it should have at least one final state, right. So, these are the basic characteristics of the finite state machine, and all the edges should be labeled, all the edges should be labeled, right, and all the edges should be directional. We cannot have a non-directional edges for the between the transition between the states in case of a finite automata. Now, non-deterministic finite automata, which I have already discussed, right, the second category of finite automata, the non-deterministic finite automata. Now, let us quickly go through the definition of non-deterministic finite automata. In some books you will also, it is also written as NFA, NFA. So, NFA, non-deterministic finite automata, is defined as again with the help of 5 tuples. So, these are the 5 tuples through which we define NFA: Q, sigma, delta, Q naught, F. In a DFA, for a particular input character, the machine goes to one state only. Please remember this point. In case of DFA, the previous category of finite state machine which I have just discussed, in case of DFA, the machine goes to one state only, right. So, it means that for every input there is a unique transition, for every input there is a unique transition, but in case of NFA this restriction is not there. In case of NFA this restriction is not there, which means that a transition function is defined on every state for every input symbol. So, it means that I can have multiple transitions for a single input. For it means that if I am in the initial state Q0, for A input I can be in Q0 also, or I can go to Q1, or I can go to Q5, right. So, the same input can have multiple transitions. This is possible, this is allowed in case of non-deterministic finite automata. Again here Q is the finite set of states, finite sigma is the finite set of alphabets which is used to make the input letters, right. Q naught is the initial stage which belongs to the Q set of states. F is the final state which is contained in the Q states, right. Now, this is the transition function. Now, this is the transition function for the NFA. You can see 2 to the power q, that is a multiple transition. With same input, I can go to different set of states. So, this transition functions make the difference for NFA and the DFA. It is a major difference lies in the transition function for the NFA and the DFA. Now, in this slide we can see that we have to draw NFA which recognize all strings ending with 0 1, right. So, this is an example of NFA, right, in which all strings ending with 0 1. Here you can see that this q 0 is the initial state, as there is an arrow which is going into the state. So, this q 0 is the initial state, right. In the initial state q 0, again we will have two types of input. The one input will be 0 or the second input will be 1, right. You can see over here that in q 0, if the input is 0, there is one transition which is going from q 0 to q 1 for this 0, right. So, my machine is going from q 0 to q 1, and for this 0 also it is going from q 0 to q 0. There is a loop for this 0 itself, right. So, this is the non-deterministic automata. It is a non-deterministic finite state machine. For single input 0, I have one transition from q 0 to q 1, and for the same input 0, there is another transition from q 0 to q 0 itself through this loop, right. So, this is the NFA characteristic which is highlighted over here, right. Now, we want to draw a non-deterministic finite automata for all strings ending with 0 1, right. So, if I have a 0, it will go to q 1 state. Next, once in a q 1 state, if I find a 1, it will go to q 2 state, which is a final state, right. So, you can see in this example, right, all the strings which are ending with 0 1, only they go to the final state, which is a state q 2. All strings ending with 0 1 will go to the final state, which is the state q 2. Now, in this slide, I have tried to highlight the characteristics of non-deterministic finite automata and deterministic finite automata, right. So, basically this slide is the summary slide what we have studied in the previous slides. If you see point number 1, every DFA is NFA, but not vice versa. It means that every deterministic finite automata is NFA, but NFA is not a DFA, right. So, the reverse is not true. This is the meaning of the point number 1 in this slide. Now, the second point says that both NFA and DFA have the same power, and each NFA can be translated into a DFA. So, I can break this point number 2 into two sub points. The first point I can say that both NFA and DFA have the same power, right. If I say that both NFA and DFA have the same power, it means that the work which is done by DFA, the same kind of work can be done by the NFA. There is no language, there is no work that cannot be that can be done by NFA, or it cannot be done by a DFA, right. So, both of them will have the same kind of this work, right. Whatever language it is recognized by NFA, the same language is recognized by the DFA also. And the second sub point says that NFA can be translated into a DFA. NFA can be translated into a DFA, right. So, it means that if we have a NFA, we can easily convert it into a DFA. The third point says that there can be multiple final states in both DFA and NFA, right. So, we can have more than one final states. The fourth point says that NFA is more of a theoretical concept. In this subject, you will see that generally we draw the DFA. NFA is not very much commonly to draw, but it is there. DFA is used in lexical analysis in the compiler. If you see at the first phase of the compiler, right. So, the first phase of the compiler is a lexical analyzer, and we use these DFAs in the first phase of the compiler, which is the lexical analyzer. Now, we have another important topic to cover over here, which is a regular expression, right. So, the regular expression can be defined as the language recognized by finite automata can be easily described by simple expressions called regular expression. So, what is a regular expression? Regular expression is the language recognized by finite automata can be described by regular expression. The language recognized by regular expression are also referred as regular languages, right. So, what can we say over here is that we can have a regular expression for all the regular languages. A regular expression can also be described as a sequence of pattern that defines a string. Regular expressions are used to match character combination in strings. Searching algorithms used this pattern to find the operations on a string. So, this is all about the regular expression. So, all the regular languages can be converted into a regular expressions. Now, in this slide we have got two examples of DFA, right. So, in this slide you can see that we have got a table, and this is the regular expression for even number of A's, and this is a DFA which recognize the even number of A's, right. Again, in this diagram you can see that the machine will start in the initial state, which is a Q0 is the initial state, right. Q1 is the intermediate state, and the important point which I would like to highlight over here is this: the initial state is made the final state also, right, because if I say that even number of A's, even 0 A's is a even number. So, the 0 A's, right. So, I have made the initial state as the final state, right. And in second example, this is for this particular language, strings with AB as a substring, right. So, all the words in which AB as a substring are there. So, this is a regular expression, this is the regular expression for that, and this is a DFA. In this DFA you can see that we have got three states Q0, Q1, Q2. Machine Q0 is the initial state, machine will start in the Q0 state. If A is the input, it will go to Q1, if B is the input, it will have a self loop. In Q1, if A is the input, then again a self loop. If B is the input, it will go to the Q2, right. Once the machine is in the state Q2, it means that it have encountered A and B. So, it will remain in the final state, right. So, this is the DFA for the strings with AB as a substring. Now, there is another example for DFA design, right. So, the example says that let us design a DFA that recognize the words that contain 0 1 as a substring, right. So, this is the question which is given to us. Now, I will quickly go through this DFA design, right. So, again the question is, so the question is, right, words that contain 0 1 as a substring, words that contain 0 1 as a substring, okay, words that contain 0 1 as a substring. Machine this A is the initial state, machine will start in the initial state, right. If it have a 0, it will go to state C. If it have a 1, it will go to state B. In state B, again it can have a 0 and 1. If it encounters a 0, it will go to state C. If it encounters a 1, it will loop back to state B. In state C, if it gets a 1, it will go to a D state, which is the final state. If it gets a 0, it will loop back. And once in the final state, any number of 0, 1 comes, it will remain in the final state, right, as we have to recognize the substring 0, 1. And this is a transition table for this DFA. In this transition table, you can see that here I have got all the states A, B, C, D. A is the initial state, D is the final state, and if in state A, if the input is 0, state A, if the input is 0, it is going to state C. So, I have written C over here. If in state A, if the input is 1, it will go to B. I have written B over here. In state B, if the input is 0, transition is up to C. I have written C. In state B, if the input is 1, it will go to B, self loop. So, I have written B over here, right. In state C, 0 to C, 1, it will go to D, D, and this star means D is the final state, D 0 1 D D, right. So, this is the transition table and the DFA for the language 0 1 as a substring. Thank you. This was all for today.